Hi everyone, my name is Ashley Tice and I am a student researcher with the Birth Outcomes in Water Research Project, which is led by Dr. Martha Rhodes. This past year, I have been researching the correlation between nitrate and nitrosatable agrichemicals in Nebraska groundwater and the risk of adverse birth outcomes. To begin with, I'll give you a little bit of an introduction and background, then I'll move on to the methods I used and the results I got, and we'll end with a conclusion and some discussion. So, according to Nebraska's 2016 Vital Statistics Report, Nebraska's rate of birth defects, which is 6%, is notably higher than the national rate of 3%, which is obviously something we do not like to see. Nebraska is also located in the Corn Belt, and agricultural practices often use atrazine and nitrogen-based fertilizers. Atrazine and nitrate have been detected in groundwater and can be present in drinking water. This is not good because when atrazine and nitrate combine under acidic conditions such as the human stomach, it can combine to form a nitrosamine called N-nitrosoatrazine or NNAT, which is what I'll be calling it for the rest of this presentation. Exposures to nitrosamines may also be correlated with neural tube defects, cleft palate, neonatal death, and stillbirth in rodents. NNAT may cause chromosomal abnormalities in human lymphocytes in vitro at low concentrations. Exploratory research showed a positive correlation between the birth defect rates and the percent of wells containing nitrate and at least one nitrosatable compound. So the purpose of my research project was to identify the relationship between exposures of nitrate and nitrosatable agrichemicals in drinking water, birth defects rates, and fetal death rates, which I did by utilizing new data gathered about fetal death rates in each county. I also wanted to better understand associations between exposure to nitrate and nitrosatable agrichemicals and the risk of adverse birth outcomes. To do this, I started off by adding to an existing dataset that contained some agrichemical information. This dataset included information about the number of wells that tested positive for each agrichemical and the total wells that were tested for the agrichemicals, and we had this data for each of Nebraska's 93 counties. And from this information, we could calculate the percent of wells positive for each agrichemical by dividing the number of wells that tested positive by the total number of wells that were tested. I created 15 new variables to add to this data set, and I combined various combinations of nitrate concentrations greater than 0, nitrate concentrations greater than 2, atrazine, DEA, and DIA to see if any agrichemicals were present in the water samples multiple times. I also, after a little bit of data manipulation, I ran correlations of all variables against the following variables: 2010 to 2014 birth weight less than 1,500 grams, birth weight less than 2,500 grams, fetal death rate, infant death rate, neonatal death rate, perinatal death rate, 2005 to 2014 all birth defects, and 2005 to 2014 National Birth Defect Prevention Study, or NBDPS, birth defects. The birth defect rate and fetal death rate for each county were obtained from the Nebraska Department of Health and Human Services, or DHHS. So like I mentioned before, I had to do a little bit of data manipulation before I could run these correlations. So one of these data manipulations I did was restructuring well data so that each well was represented in the data analysis only once. To do this, I took advantage of the clearinghouse numbers. So when we did our queries from the National Quality Assessed Agrichemical Contaminant Database for Nebraska groundwater, each well is given a clearinghouse number. So no matter how many different agrichemicals or how many different times the well is tested, it always has the same clearinghouse number. So I used the clearinghouse numbers to make sure that each well was only represented in the data analysis once. So I ran these correlations using the Kendall-Tau correlation coefficient test, and I used this test because not all variables are normally distributed, and I did all this analysis in SPSS. From my results, I got this nice little table that I put up top, and all the agrichemicals had significant positive correlations except for 5. So you can see from this table that 3 agrichemicals have significant correlations with less than 1,500 grams birth weight. 7 agrichemicals have significant correlations with less than 2,500 grams birth weight. 3 agrichemicals have significant correlations with fetal death. 1 agrochemical has a significant correlation with infant death, 2 agrochemicals have significant correlation with neonatal death, and 17 agrochemicals have significant correlations with all birth defects. 3 agrochemicals have significant correlations with NBDPS birth defects. There were 0 agrochemicals that had significant correlation with perinatal death rate, so I just eliminated that from the results. So we can look at these results and the correlations to understand the impacts of drinking water containing nitrate and nitrosatable agrochemicals and adverse fetal outcomes, such as fetal death, perinatal death, infant death, neonatal death, and the birth defect rate. While we cannot infer causation because of the correlation, we can use these results and the knowledge that agrochemicals have significant correlations to generate future hypotheses. This project also allows us to better understand associations between exposures to nitrate and nitrosatable agrochemicals and the risk of adverse birth outcomes. Previous literature and research had mostly looked at single compounds, while this research looked at mixtures of compounds. Another result I found was that there were 97 pairs of significantly correlated agrochemicals, which is a limitation of the study because contaminants could be surrogates for one another, but we do not know if the agrochemicals are causal in an increased risk of birth defect, so we do not know if these agrochemicals are confounders for sure. The only thing we can do because of this is compare areas where surrogates are present to areas where the surrogates are not and see if the agrochemicals have an equal effect on the outcome. Finally, I would like to thank several people for their help with this project. It would not have been possible without them. Dr. Cheryl Bessler for her statistics knowledge, UCARE for funding this project, and Colleen Steele of the Conservation and Survey Division who ran our well query for us, and of course Dr. Martha Rhodes, my project mentor.